Hello, welcome to the first lecture that we try another mode to deliver the lecture. So first, I would like to explain what happened on Thursday. So basically, the WHO announced the COVID-19 as the pandemic, and on that day, and also you probably see a lot of actions taken by governments all over the world. So given the escalating scenario of this potential virus and the fact that uh, we are going to lecture in a closed room um, for 2 hours. So I think for the safety of the both for the staff and also for the students. So we are actually thinking that we probably eventually will move on to this kind of online delivery mode, um, just as many of the universities in the states are already doing, and also not to mention that in China, right? So basically, we actually opened up a poll, and uh, by now the poll result is actually out. So as you can see, 95% of the students voted. Um, that's the majority of students in Australia, because we got around 200 um, stranded in China, and the total enrollment is 400 plus. So basically, you can see that the turnout of the vote is for students in Australia is pretty high, and the majority of them actually think that we can actually do the pre-recorded videos. So actually, I went to the lecture theater with the mask, and also I saw some students also wearing the masks. Um, and so basically, in total, there are about initially there are about 17 or whatever. So at the end of the day, I think by the time I left, after 20 or half an hour, so basically there are 23 students in the coming to the lecture. So basically compare with the 200-ish enrolled. So basically, but again, I didn't really look into the number, how many of them are actually enrolled into the web stream or versus the physical stream. But I think it's relatively okay for us to move on to this kind of online delivery mode. Uh, Basically, there are also some kind of good suggestion from the students. So what I'm trying to do is that first of all, I'll try to record the videos and then release it, uh, you know, on time. This video was late because I just want to wait for the poll to come out and see if what's the majority of the student thinking. And so basically, it will be released at the same lecturing time, and uh, also for the safety of the tutors and also the students. So we were not going to host the physical consultation. We do have them every Friday. So basically, I'll uh, probably use Zoom. Again, in terms of software and platforms, I'm open for suggestions. But the basic thing that we need to potentially accommodate potentially hundreds of concurrent viewers. So basically, we will try to host the conversation online. There are different kind of formats we can do. We can either set a fixed time, or um, some students suggest that we can actually compile a list of questions of the week, probably due to through the forum or whatever. Then we can actually do some kind of discussion online. So that will actually be real time. So this will also hopefully satisfy um, the demand of 5% of the voters, and also some of the students who actually come to the lecture actually express that they want some kind of interactions. So hopefully this will serve all of the different demands. Okay, so I think that's all for now. And if there are any logistic issues, just feel free to let me know. You can email me, or you can send a private. I prefer send you send a private message through the forum. So basically, we can go from there. So let's come back to the content of lecture. So today we are going to do two of the clustering algorithms, basically two general approaches of the clustering algorithms. Okay, so the first one will be partition-based algorithms. We already mentioned some basic ideas, concepts at the end of last lecture. And the second paradigm we are going to cover is the so-called hierarchical clustering algorithms. And we probably will leave the graph-based, which is spectral clustering algorithm, to the next lecture. Okay, so just to recap, the partitioning-based method is actually a very generic way to do the clustering. So the general idea is that no matter what kind of things you do, you are going to partition n objects into k clusters, provided that you actually predetermine the k to be used. Okay, we'll talk about how to select k later. So no matter which partition you use, it's going to be like this. If you insist on k clusters and they are all equal to each other, so basically there is no hierarchical this kind of notion between the clusters. So a visual explanation is something like this. Although if you want to do it more accurately, it's going to be like, for example, this is one cluster, this is another cluster, let's say, and you need to include everybody in, right? So nobody should be left out. Okay. Again, the cluster boundary is, I just hand draw it. It's not necessarily like this. Only there is most of the clustering algorithms do not really have a physical boundary, although some of the algorithms do induce a boundary. Basically, all we care is the membership. So for each point, for example, for each point, at this point, you need to know which of the cluster it falls into. Right? And the last time we actually talked about the general idea is that whenever you have a group of people belonging to one group or one cluster, um, um, what we are going to do is to select a representative or select a center. Okay, I would like to use representative because there are actually more advanced algorithms which select several representatives, and they are not necessarily in the center of the cluster. Okay, but since we are dealing with the basic version, like the k-means and all the other simple variants, usually there are some notion of center. Okay, if you know, there are actually different versions of centers. So basically, we are going to select a center or representative such that we can actually use the representative to represent each and every point in the cluster. Okay, so we come up with the formula which is here, which essentially says, okay, the cost or the sort of like the imperfectness of a cluster is the difference between each and every data point and its center, and take the L2 distance and raise it to the power 2 and sum them together. So this is essentially some notion of L2 norm. We already talked about the LP distance, right? So LP distance using LP norm, and sum them together for each and every point. And then this is actually the cost of one cluster, C1. So for this, we can actually calculate cost of C1, and you can do the same thing for cost of C2, and you can do this for cost of C3. And if you sum them together, you actually have a total cost. So if you think about it, total cost is a function of a number of variables. Okay, the first variable, and arguably the most important thing, is actually the membership. So we need to know, for example, for this point, each point, which cluster it belongs to. Right? This determines to which representative will actually be the corresponding one to calculate the cost. The second thing is essentially given a cluster of all its members, what is the representative we're going to use? So the second question, let's say I still write center, okay, just to write simply. last time we actually mentioned that the center, it turns out that if we use our cost is based on L2 distance, the best center is the geometric center of the points within the cluster. So last time we actually have a simple example where, let's say for two-dimensional case, if one point is 3, 5 and the other one is 2, 6, basically their center, geometric center, will actually be the average points on each and every dimensions. So basically the center will be 2.5, 5.5. So notice that the center is not necessarily within the, it's not necessarily one of the data points. Okay, so this might cause some problem in some case because not all the vectors actually are meaningful. Okay, you can think about examples like this. But anyway, I mean, that's the way we actually do it. And it turns out that this one will actually minimize the cost. So in other words, if one is decided, we can actually use the center to minimize the total cost. Okay, cost I is the cost in each and every point. So the center I actually depends on the membership. Okay, so for the k-means clustering, this is actually settled. So we already talked about some of the cost. Now the problem, once you see this, you can actually see that now the only variable is actually this one, membership. So as long as we can figure out the membership, we actually know the cost. So the optimization problem will actually be trying to find a configuration of the membership and such that the membership actually achieve the minimum cost. Right. This is almost like you have different road to travel on a map, right? There are certain constraints, like if you think about each road segment as a variable, you can, if it's 1, it means you traverse this segment of road, and the 0 means you don't traverse. Basically, every path from A to B, basically corresponding to a solution over all the road segment. Although it's going to be a very high dimensional binary vector, but basically the so-called short path is actually you want to find such a path such that their total cost is minimum, or equivalently each path corresponding to a particular assignment to the road segments. Right, so that's similar idea. So we want to find. So this is an optimization problem, and as you will see again and again in machine learning or data mining, or in most of computer science, we actually need to model a physical problem or real problem into some kind of mathematical problems. And one very powerful paradigm is actually to cast this as an optimization problem, and especially numerical optimization problem, because there are actually discrete optimization problems, usually using combinatorics to solve them. But numerical ones, there are actually lots of tools, and in the very worst case, I mean, we can actually use some kind of numerical approach to approximate the solutions. So we don't really get a closed form solutions, but we actually can get a value which almost minimize or maximize some kind of functions. Basically, the difference between the actual root, if you like, or the actual optimal solution versus our approximate one is so small, such that it basically can be ignored, just like in reality. Every measurement have their errors. Okay, so it turns out that this problem is actually NP-hard for a wide range of cost function and settings. Okay, people actually, if you know, in operational research, OR, people actually study different versions of this problem. Of course, they are not doing clustering, but they are actually doing something like, for example, you want to, for example, these are actually residents, right? Each one is a household, and you might even have a weighted version because depending on the size of the family, and you want to, let's say, build 3 hospitals or 5 stations, such that the cost will actually be the maximum. For example, if I build a fire station here, for this C2 cluster, you can actually find what's the travel distance or whatever travel time from each and every household in this cluster 2 to this proposed fire station, and you get the maximum. Maximum is actually the longest time it takes for anybody in this cluster to reach corresponding fire station, right? So if I'm going to have the budget to build 3 fire stations, right? Where to build them such that the let's say the maximum of the worst case uh, travel time um, among all the 3 clusters or all the 3 communities to any of the fire stations is actually minimized. This actually will reduce the risk of property loss or people's lives at danger. Right? So basically, it turns out that for a wide range of cost function and settings, basically it's NPR. So NPR essentially means, and most of us actually believe that this means there is little hope to find a polynomial time algorithm to find the exact maximum or minimum. Okay, for our case, it's the minimum cost solution. So, and if you really stick to the exact solution, the only thing you can actually do is actually to um, do exhaustive enumeration. But it turns out that this number is actually a special number called the Stirring number of the second kind. Again, it's not important, but the whole idea is that in terms of the uh, order of magnitude, it's going to be k to the power of n over k factorial. But basically, it's going to be k to the power of n. Okay. So for any substantial k, even for k equal to 2 or let's say 3, it's like a small constant. So if the smallest k you can do is k equal to 2, right? So this will actually be theta 2 to the power of n over 2. Right, so this will be theta 2 to the power n minus 1. So basically this is exponential in the number of points. So this is definitely not infeasible. So that's why there are different kind of approximation schemes or heuristic methods. One of the most popular one, and we'll talk about the reason later, is actually called k-means. And this is actually an instance of so-called EM algorithm. EM is called expectation maximization. We'll actually have slides dedicated to explain EM later. So basically, at this stage, you don't need to know too much about EM. Basically, EM is a way to deal with latent variable and trying to do optimizations. Okay, and there are actually many variants. We'll quickly mention some of the variants and comments on their strengths and weaknesses later. But first we focus on k-means. So, what is a k-means? So for the k-means algorithm, the idea is very simple. So what they do is that they actually initialize k centers randomly. Again, provided that k is given. And once you determine the center, we actually enter into loops. Okay, so there are certain kind of stopping conditions, and in each iteration of the loop, what we do is that since you already select centers, let's say this is the 3 centers, right? For each and every point, now this is my O1. Now I should decide which cluster should I belong to. Okay, it's almost like these are the 5 stations or hospitals, and you often should go to the nearest fire station or hospital. Right? So basically, you assign each object to the cluster with the nearest center. Okay, so in this case, you can see that if you look at the L2 distance, most likely O1 belongs to this cluster. Then you do the same thing for, let's say this is O2, and this is O3, and let's say this is O4. Okay, most likely they're like this. And then you can see that the membership of this cluster actually consists of O1 and O2. Remember that the center is really dependent on the membership. Okay, because once we fix the membership, we can always select a better representative for the current group of members, just like voting. Everybody try to vote to find the solution which is good for them, and if you aggregate over all the members, that's actually, in certain sense, that's the best for the group. So intuitively, in this example, you can see that the geometric center will actually be this one. So you actually remove this one, and you actually go there. Right. So basically, this is for this center, and for this center, if there is only one point, let's say here, basically this one will actually be, so this one actually will be moved to here, just overlaps, that's the same point as O3, and the same thing. Okay, and then the first iteration is done, and you actually move on to the next iteration, and so on and so forth. Okay, so what are the stopping conditions? There are basically two different possibilities. One is that it can be shown that this algorithm will actually converge. Okay, although at a later stage it might converge slowly, but eventually it will converge. And typically what you do is that you actually test whether the current solution and the last solution, their quality only differs by a little bit. Okay, the quality is essentially the cost. So by convergence will actually mean that the cost will actually never increase. It's when it converges, it stayed at the same cost, or in general, it will actually gradually decrease. So if the decrease the cost, if you measure the amount, it's actually smaller than certain epsilon, let's say, then you can actually stop. So that's the scientific condition to stop the iteration. But in practice, a very common way is that you actually prefix the number of iterations, or you prefix a particular time. Let's say run for 5 minutes, or run for 20 rounds. Okay, this is mainly because this algorithm does not guarantee the optimal solution. It only guarantees, even when you converge to a solution, it's going to be a solution which is the so-called local optimal solution. Okay, so if that's the case, it's actually will be better off if you run the algorithm multiple times, because each time the center will actually be initialized differently, and it will actually be converged to different center. Okay, so graphically, although this is not the best thing, it should be if you like, this should be a 3-dimension. It's not 2-dimensional, like if the feature vector is actually d-dimension, so this should be a d-dimensional plane, and that's the cost. Okay, so the whole space is actually d plus 1 dimension space. And again, forget about this one. I'm not going to draw a 3D plot. Yeah, so just pretend this is actually d equal to 1 for data points. The general idea is that you might have values like this. So if you start from here, let's say this is your random start one, basically it will only decrease. It will never, the cost will never increase. So you know that it's going to end up in here. Okay, but on the other hand, if you start from here, don't be so. Let's say you start from here, then it will actually grow down and come to here. Okay, and if you try it again from here, you actually will go to here. So eventually, if you run it 3 times, you will get it here, here, and here. So you take the minimum. In this case, it's this one. So this will actually be better off than spending more time trying to get a very small, to get a loop to converge to a local minimum value. Okay. So the last question is, what are the final clusters? Okay. So I think you should be easily you should easily figure out what are the answers. Okay, and I leave this as a very simple exercise for you. So this is another example to illustrate how the algorithm works. So again, this is the case where we have a number of points represented by diamonds, and we initially randomly assign two clusters like these red dots. Okay, and based on these red dots, we're going to assign points to the nearest cluster. So the reason you actually have different color, let's say, is roughly right. So everything to the left of the dash line is actually belong to the first cluster. Let's say C1, this is C2. Okay, and what you do is that you do the assignment. Yeah, basically you end up with this one, and once you know the membership, so this is actually a graphic illustration of the membership of clusters. You actually determine the red points to be the geometric center of all the members. Okay, so you updated the centers. Then, so this is end of the iteration 1. Okay, so basically, this is iteration 1. Then you move on to iteration 2. This is the iteration 2. Okay, in iteration 2, what you do is that you do essentially the same thing because it's a loop. So so now you actually have the new red centers, right? So what you do, and these are the points. So basically, you actually assign points to the closest center. So the red dots are not shown, but basically you can see that this point is now allocated to this cluster because it's closer. So at the end of the day, you are going to see these two guys, and essentially here, right? From here, you actually updated the new center. So if you compare this one and compare this one, just remove this one. So if you compare these two, this one is actually at a 3.5, 5 point something, and this is actually 3.5, and it's close to 6. So it actually moves slightly upwards. Okay, maybe towards the right a little bit because basically this point actually is belong to the center. Okay, although the rest of the membership remain the same. So basically, it's going to be the x-axis should be slightly larger than this one, but you can't see it. And then it actually go back. Of course, I mean, the iteration 3 is not like this, but you get the idea. So you actually do this round and round until certain stopping condition is met. Okay. So what's the running time? The running time is actually t times k times n. So first of all, k times n is the cost per iteration, because in each and every iteration, you actually need to calculate the distance of every point to the k centers. So to be strict, it should still have a d, because most of the distance actually take, I mean, to calculate distance between 2 points in d-dimensional space, generally speaking, it takes OD time. You might be able to define some funny distance, which is have a even higher, time to calculate distance, or even lower. It doesn't matter. But if usually the reason we didn't write O is because usually we think D is actually a constant. You can't change the feature vector as far as the clustering algorithm is concerned. So what you do is that you actually yeah, you just omit the D here. If you want, you can add the D there. So K, so for each and every point N, you need to calculate the distance to the K centers, and then choose the minimum one. And once you have done that, essentially in each iteration, you actually do Kn, if you like. K, again, everything is big O, so I want to write big O. Plus, then you actually need to recompute the center. But there are, if you think about the programming, you can actually, because it's geometric center, so all you need to do is to accumulate the sum of each and every dimensions. So you only need to keep d counters or accumulators, d accumulators, basically memory cells, and during the k and d process, you actually make sure you actually have the sum on each and every dimension. So basically, and you only need to have another d cost to calculate the center and the times k. Okay, but again, this one actually was dominated by k and d, so that's why this one is actually removed. And finally, you actually have a t. T is actually how many iterations you have. T is how many iterations you have. So the final cost is t, k, and d, if you like. Okay, so this is actually, I would say, almost the best you can get. First of all, if you forget about all the other things, like k is usually chosen by user, let's say t is actually can be chosen by user. So the whole algorithm is actually ON. ON is actually linear in the data set size. So in other words, if you have 1 million in data points, if it takes 1 minute to run the k-means clustering, given the same k and t, so you can expect that if I give you, let's say, 100 million, the running time will be 100 minutes, roughly. Okay, it doesn't scale like quadratically in the number of points, which will be bad. So if you compare with other algorithms, even in the same category, basically they are going to be, this is all superscript. So basically the algorithm will in general be n squared, and this one is actually s squared, and s is usually n divided by some like large constant, let's say L. Okay, so if f squared, it's going to be n squared over some large constant. So if you really argue strictly, basically n, it's still n squared. So if you have, even if you have 1 million points, n squared, any, if you just do a loop of, let's say 1 million over 1 million divided by 2, do a very simple loop over 1 million element arrays, that's still going to take a long time. Not to mention that if you grow to 100 million, the running time actually grows to the, so basically it grows 10,000 times higher. So even if the previous loop over, double loop over the 1 million actually takes, let's say, 1 second, that's going to take 10,000 seconds. So basically, that's going to be like tens of hours at least. So you can see the growth actually is really not friendly to large data sets. Okay, so that's, I would say that's the most important reason, that's the most important strength of the k-means algorithm. K-means algorithm, as you can see later, there are actually lots of weaknesses, but it turns out that the efficiency alone and the scalability alone is the biggest benefit, because for real large-scale datasets, there's no easy way for you to run other algorithms. They will all run out of time. Okay, so what are the weaknesses? So the weaknesses are that it's only applicable when mean is actually defined. So as we said, the center need to be, they by default they use geometric centers. But if we have categorical data, remember that we actually talk about different ways to handle the data. For example, for rank normalized data, if you get a mean point, the center actually means you want to have a student whose let's say ranking is 3.3. So what does it mean? So, and not to mention that if each and every data point is a string, right? How do you do the average of a bunch of strings? So there are different solutions, including, for example, the PAM and other solutions we are going to talk about. And also the other thing is to deal with K. So K has to be given. So how to fix the case? So in practice, there are actually ways to, there are different proposals. For example, we haven't talked about classification yet, but basically there are ways, this is the problem of model selection. So you can imagine that you can use any K. You can use K equal to 2, K equal to, let's say, 28, K equal to 200. Each of them will actually give you a different cost, right? So K equal to 2, the final cost, let's say if it's 1,000, K equal to, let's say, 20, so what will be the cost look like? Okay, it can't be 2,000. It can't be anything more than 1,000, right? Again, it's not saying it can't. I mean, the probability will be very low, especially if we talk about the optimal solution. If we really exhaust all the combinations, basically, typically you are going to see that the cost of using more cluster will actually only decrease or remain approximately the same, with some kind of fluctuations because the algorithm is a randomized algorithm. So let's say this is actually 100, and the K to 200, the cost might be, let's say, 10. Okay, this is just illustration only. So if you don't be careful, you probably will say, okay, I choose this one. If you keep on choose this one, you can always make sure the cost is actually 0. Right? You can, if there is no limitation on K, you can always make sure the cost is 0 for whatever functions you use, as long as you use some kind of distant functions. Right? If K equal to n, which means everybody belongs to their own cluster, the cost will be 0. But it has absolutely no benefit. Right? I mean, the whole point of the clustering is to group things into smaller number of clusters. So you can imagine that in the model selection or in many cases, I mean, there are different ways to do that. One way is that you actually have certain prior over the case. Okay, you believe, let's say there are knowledge to say, okay, there are, let's say, you know, there are, one of the example is that if I give you a bunch of people, their height and weight, right, or some other attributes, and again, this is not necessarily politically correct, but just to make example simple, just assume that we have, let's say, two genders, male and female, and so basically we know that the group of students actually have to belong to one of the groups. Again, just assume this is the assumption or constraint we have to abide by. Then basically you can actually put a high preference over K equal to 2, or if you believe there are other choices, but K equal to 2 is more likely, then you can actually say, I believe K equal to 2 have maybe 80% of the cases to explain the current mixture of people's data, or you can actually say, okay, K equal to 3 maybe have 10% probability, and so on and so forth. So this is one way. Another way is to think about that as you increase K, the cost will definitely be smaller. Okay, you want to find a sweet spot where the increase of K is actually, justified by bringing down the cost substantially. Right? Because later, if you really draw the figure, it's going to be something like this. It's going to plateau once K is large enough. Okay, so again, some of the people actually choose K equal to here, or some of the people actually choose K equal to here. It doesn't matter. So what you do is that in practice, because K-mean is relatively efficient, you actually try different kind of K values. Let's say you try from K to 2 to, let's say you can increase by, let's say, 3 or 5 initially, and then you find a spot. Basically, let's say if you try the first one here, and you can do the binary search and then try this one here. So basically, there are ways to empirically choose the best case. So that's something you can deal with. Okay, just pay additional cost. Another thing is that k-means actually cannot deal with noisy data and outliers. Why? This is because if you look at the cost function, the cost function is actually a group of, so basically it's this one. You actually have the square, get rid of this one. So you actually have the uh, uh, raise the difference between a point with the center with the square. So basically, if one of the xj's are really far away, let's say if you have this point and you have this point, for whatever reason, let's say if you have to put them into one groups, you would imagine that the center now will actually be something somewhere around here, and that's going to screw up the entire cluster. Okay, so if you have, this could be a mistake. For example, you misplaced the decimal point, or it could be an outlier. I mentioned the platypus as one categorical outlier. Right? There are a lot of exceptions. Right? Um, so basically, there are also ways to deal with it. One of the things is that you use more robust kind of cost functions. For example, if you use L1 norm, it's more robust to noisy and outliers. But more typically, what you do is that you actually manually run some kind of outlier detection algorithm. Okay, we didn't talk about it, but that's actually one of the common things you need to do in the data cleaning part. And presumably, if we get data from data warehouse, the data has already been cleaned. You certainly don't want erroneous sales data to get into your warehouse and then later get into your analytical pipeline. And the final problem is that it doesn't deal with non-complex shapes. Again, this is huge because of L2. If you remember, we actually draw this is L1, this is L2, and finally this is L infinity. So as long as LPP greater than 1 or equal to 1, the shape is actually convex. Okay, so in theory, you can actually use P smaller than 1, but again, it's not very common. Okay, uh, so basically, that's the limitation. But again, in many real cases, we mainly deal with high-dimension data, although we illustrate it using two-dimension data, which is easy to visualize. For high-dimensional data, the best thing I can say that I don't think many of us actually know what should be the correct shape of a cluster. There are in high-dimensional space there are, so the geometry is very different from low-dimensional space. Okay, um, won't go too deep into it, but the whole idea is that um, whether the convex non-convex shape cluster really exists or it's significantly better than convex shape, we don't know. Okay. So and also, I mean, for the high dimensional space, because D is actually large, so D is large. Um, Basically, it's even harder to use any other algorithms. So k-mean is sort of like the only way you can use if you really don't want to use other approximation schemes like sampling or other things. Okay, so we quickly talk about there are different variations of k-means. They actually differ in how to select the initial k-means and how to you can plug in different kind of distance functions. So this is essentially distance functions. But remember, whenever you change this distance function, the center. Actually, one thing not mentioned, yeah, this is cluster means, but essentially it should be really be the center, or I would prefer representative. So how to choose one representative or several ones for each and every cluster. This actually depends on the distance. Uh, and the cost function. Okay, so basically that's the thing you can deal with. So how to handle categorical data? Remember, categorical data is more like the simplest example is the color, the let's say the profession of a person, and so on and so forth. So what you do is that you actually can use something called a mode. Mode is actually of a distribution is actually of a discrete distribution is essentially the most frequently occurring value. Okay, so um, you can replace means using modes and so on and so forth. Uh, we won't go too much into this, but basically uh, it's not the most common way nowadays because with the deep learning especially, we can actually use other ways to handle this problem. But in the early days, if you stick with the discrete space, that's probably one of the best things you can do. Now we actually talk about one uh, very nice work. Um, it's actually published in 2007, but it has already been widely used in most of the k-means, reasonable k-means implementations. For example, if you use scikit-learn, it actually have the k-means library, and basically there is a, I think the default initialization is the k-means plus L. Okay, so the algorithm is very simple. If you only look at the algorithm itself, the analysis, SODA is actually one of the best conferences in theoretical computer science. Basically, they prove a lot of nice results. Basically, it's a very simple initialization routine to select the initial centers because that's the only randomness in the whole algorithm. Okay, if you don't use any other approximation schemes that guarantee to find a solution that is O log k competitive to the optimal k-means solution. So O log k competitive means if I can find the optimal solution, which is actually an NP-hard problem, but just assume that we know the optimal solution, the solution obtained by k-means plus plus have a high probability um, that it's actually within O of log k factor of that. For example, the optimal solution have a cost equal to 1,000 and the k equal to let's say 2, let's say 4. Okay, and this is log 2. Okay, so this is actually something like O2. Again, just assume the big O actually the constant factor is 1. So the k means plus plus the cost is highly likely to be around let's say 2,000. Okay, that's not really the best thing uh, if you just look at numbers. But for theoretical people, this is actually much better than if you don't use this scheme. There is absolutely no guarantee. I mean, cannot guarantee the local minimum. Just as if you remember, we draw a one-dimensional curve. Um, there won't be any guarantee that this kind of things will actually happen. Okay, but this one actually occurs with this kind of worst case guarantee. So the algorithm is actually very simple. So before k-means plus plus, there is another um, widely used initializing method. I think it's Gonzalez or whatever. It's actually a Spanish name or named after a person. So, but the general idea is that whenever you find a cluster, right? So, um, so if you have a point here, and points here, and some points like this, right? So, what's the uh, so the previous method actually what they do is that they randomly select a point. Let's say random select this point, and let's say you want k equal to 3. So what you do is that you select this point, and the next point you select is the furthest point from the current center. So so most likely it's going to be this one. So C2, center 1, center 2. Okay, and the third one will actually be so for each one. Let's say you consider this point, right? You actually have the distance d1 and you have the distance d2, and you want to make sure that this point is not too close to any of them. right? The worst point you select is somewhere just around it. So basically, you want to make sure that D1, so which is the minimum distance of OI to all the CJs, is actually maximized. So you actually want to get the argmax. The only variable is for OI belong to all the data points. Okay, so you consider all the points such that OI to, so basically, yeah, this is minimum over J. So OI to the center J's distance over all the current selected centers is actually maximized. It's a mouthful to say this, but the general idea that you don't want to select a group of centers such that some of them are actually very close to each other. Uh, Basically, if two centers are close to each other, you are wasting the capacity of the model. Basically, you can actually achieve similar results, similar representative power by using only one of them. Now, the only difference of the k-means plus plus is that the first one is actually selected uniformly at random, so that's the same. Now, for each data point x, you compute the dx as a distance to its nearest center. So that's actually the similar things as this one. This is the minimum. Minimum is the nearest center. So you calculate dx, but instead of always choose the point which give you the maximum dx, what you do is that you actually consider dx to the power of 2 for each and every point, and this will actually define a distribution. So this will actually become like it's almost like the share, right? So and then you do some kind of random drawing or doing some kind of voting. So basically, you can convert now each every point. Let's say for point 01, 02, ON. Let's say this guy have 2 to the power of 2. This one is 3 to the power of 2, and then let's say this is let's say 75 to the power of 2. So the whole thing here actually defines a distribution. It looks like this. It's a discrete one, so it should be drawn like this. You get the idea, okay? Then what you do is that you actually randomly sample one point within this distribution. So in other words, if you this ON has the best chance of being selected, actually a large chance because it's squared, right? But even the nearest point still have certain chance of being selected. Okay, this is actually a widely used tricks in randomized algorithms. The general idea is that if you randomize your decisions, okay, it's pretty hard for your enemies or for the adversaries to pick up worst case scenario against your algorithm. Okay, so that's the common way to achieve some certain kind of guarantees. So you do this. So this is actually one way to select one center. Then you loop to select all the rest of the centers. Then the rest of the algorithm is the same as the normal k-means. So it's a very clever, and again the initial sampling whatever is a little bit expensive, but usually this results to much better, you know, uh, clustering results and potentially less number of random initializations you need to try to get reasonably good solutions. Okay, so let's have 10 minutes break. Then we look at how to interpret k-means in different ways. We talk about looking at the k-means as a matrix factorization problem. Later, after we finish the clustering, we'll talk about the EM, and you can see that k-means can be also cast as a EM algorithm.